Assalamu alaikum and welcome to lecture number 20 of CS317 Operating Systems. I/O Management uses chapter 11 of the William Stallings book. In the last lecture, we looked in detail at design issues involved in the I/O function of an operating system. We discussed the logical structure of the I/O function. We understood the concept of buffering. We delved into different forms of buffering. We discussed disk scheduling. Now we will talk at length about disk scheduling. Let us first revise the disk performance parameters that we saw in the previous lecture. We have looked at different components of disk performance, which are seek time, rotational delay, transfer time, additional I/O device and channel delays, and RPS miss if applicable. Now I will walk you through an analysis of disk performance. Consider a disk with advertised average seek time of 4 milliseconds, rotation speed of 7500 RPM, and 512 byte sectors with 500 sectors per track. Suppose that we wish to read a file consisting of 2500 sectors. Case 1. The file is sequentially allocated. Let us assume that the file is stored as compactly as possible on the disk. This is known as sequential allocation. Remember that the file has 2500 sectors and each track has 500 sectors. So the file will occupy 5 sectors. The time to read the first track is as follows. Average seek is 4 milliseconds. Next will be rotational delay, which will be 4 milliseconds. We have used the formula 1 upon twice of R. R was in revolutions per minute, so we have changed it into revolutions per second by multiplying it with 60. This is the average rotational delay. We read 500 sectors in 8 milliseconds. The rotational delay is for 180-degree revolution. For a full 360-degree revolution, the time will be twice the average rotational delay. So the total is 16 milliseconds. This is for the first track. Once the first track comes under the head, the remaining tracks can be read with essentially no seek time. Then at most we need to deal with rotational delay for each succeeding track. Thus each successive track is read in 4 plus 8 equals 12 milliseconds. We are adding the average rotational delay and the reading time of 500 sectors. To read the entire file, the total time is the time of the first track, which is 16, plus 4 times the time of any other track, which is 12, and the total time is 64 milliseconds. Case 2. The file is randomly allocated. Now let us calculate the time required to read the same data using random access rather than sequential access. That is, accesses to the sectors are distributed randomly over the disk. For each sector, we have average seek equal to 4 milliseconds, rotational delay equal to 4 milliseconds, and we read one sector in 0.016 milliseconds. We read 250 sectors, that is half the disk track, in 4 milliseconds. So one sector will be read in 4 divided by 250 milliseconds. So the total is 8.016 milliseconds. To read the entire file, total time is 2500, which is the number of sectors, into 8.016, which is the time for one sector, and we get to 20,040 milliseconds. Compare that to 64 milliseconds in case 1. It is clear that the order in which sectors are read from the disk has a tremendous effect on I/O performance. Analysis of random scheduling. Consider the typical situation in a multi-programming environment in which the operating system maintains a queue of requests for each I/O device. For a single disk, there will be several I/O requests, reads, and writes in the queue made by various processes. If we selected items from the queue in random order, then we can expect that the tracks will be visited randomly. The performance of the disk I/O system will be as poor as possible. This random scheduling is useful as a benchmark against which to evaluate other techniques. To improve matters, we need to reduce the average time spent on seeks. We will discuss the following disk scheduling policies in detail. First in, first out. Priority. Shortest service time first. Scan. C-scan. N-step scan. F-scan. The simplest form of scheduling is first in, first out, or FIFO, which processes items from the queue in sequential order. This strategy is fair because every request is honored in the order received. If there are only a few processes that require access, and if many of the requests are to clustered file sectors, then we can hope for good performance with FIFO. This technique often approximates random scheduling in performance if there are many processes competing for the disk. Here is an example request queue. A disk has 200 tracks from 0 to 199. The disk head is initially located at track 100. The requested tracks in the order received by the disk scheduler are 55, 58, 39, 18, 90, 160, 150, 38, 184. Use FIFO to schedule the above disk requests. So the starting track is 100, and from track 100 the head goes to track 55 and covers 45 tracks. Then it goes to track 58 and covers 3 tracks. Then it goes to track 39 and covers 19 tracks. Then it goes to track 18 and covers 21 tracks. Then it goes to track number 90 and covers 72 tracks. Then it goes to track number 160 and covers 70 tracks. Then it goes to track number 150 and covers 10 tracks. Then it goes to track number 38 and covers 112 tracks. Finally, it goes to track number 184 and covers 146 tracks. Total tracks traversed are 498. These are 9 requests, so the average seek length is 498 divided by 9, which is 55.33. This is how the head moves for FIFO. The next scheduling strategy is priority. With a system based on priority, scheduling is outside the control of disk management software because priority levels are assigned by the operating system. The disk management software is fed requests according to the priority of the process making them. The requests of higher priority processes are sent to the disk before the requests of lower priority processes. This approach is not intended to optimize disk utilization, but to meet other objectives within the operating system. Often, short batch jobs and interactive jobs are given higher priority than longer jobs that require longer computation. This allows a lot of short jobs to move through the system quickly and may provide good response time. However, longer jobs may have to wait excessively. Furthermore, to counter this policy, the users can split their jobs into smaller pieces and beat the system. This policy performs poorly for database systems because successive requests are scattered across the disk, generating large average seek length. Shortest service time first, or SSDF. The SSDF policy is to select the disk I/O request that requires the least movement of the disk arm from its current position. Thus, we always choose to incur the minimum seek time. Of course, always choosing the minimum seek time does not guarantee that the average seek time over a number of arm movements will be minimum. However, this should provide better performance than FIFO. Because the arm can move in two directions, a random tie breaking algorithm may be used to resolve cases of equal distances. The example request queue is the same, but we need to use SSDF to schedule the above disk requests. We start from track 100, then go to track 90, then 58, then 55, then 39, then 38, then 18, then 150, then 160, then 184. Total tracks are 248. Average seek length is 27.56. This is how the head moves for SSTF. Problem with priority and SSTF. Both priority and SSTF can leave some request unfulfilled until the entire queue is emptied. There may always be the case when a newly arrived request is chosen to be served before an existing request in the queue. When the system constantly chooses incoming requests, the old requests in the queue start to starve. Let's talk about scan. A simple alternative that prevents this sort of starvation is the scan algorithm, also known as the elevator algorithm, because it operates much the way an elevator does. With scan, the arm is required to move in one direction only, satisfying all outstanding requests en route until it reaches the last track in that direction. If the arm moves in one direction only, satisfying all outstanding requests en route until there are no more requests in that direction, this refinement is sometimes referred to as the look policy. The service direction is then reversed and the scan proceeds in the opposite direction, again picking up all requests in order. The example request queue is the same. We have been told that the initial direction is of increasing track number, and we are asked to use scan and look to schedule the above disk requests. We start from track 100 and move outward. So the next track is 150, then 160, then 184. Since we are using look, this is the last pending request in this direction. We will not move forward, but we will change direction. So the next track is 90. If we were not using look, then from 184 we would have gone to the last track, which would be 199, and from there we would have moved to 90. So we move to 58, then 55, then 39, then 38, then 18. Total tracks are 250. Average seek length is 27.78. This is how the head moves for scan with look. Analysis of scan. The scan policy behaves almost identically to the SSDF policy. Indeed, if we had assumed that the arm was moving in the direction of lower track numbers at the beginning of the example, then the scheduling pattern would have been identical for SSTF and scan. However, this is a static example in which no new items are added to the queue. Even when the queue is dynamically changing, scan will be like SSTF unless the request pattern is unusual. The scan policy is biased against the area most recently traversed. Thus, it does not exploit locality as well as SSTF. As the head moves over the disk, it moves away from its current position. So even if a request is pending just one track behind the head, if the head moves in the forward direction, it will not go back to serve this request. Let us say that the head is on track 10 and it is moving to the outermost track, and a new request arrives for track 12. An old request is for track 50. Scan will move the head to serve the request on track 50 and go over 40 tracks, ignoring a request only 2 tracks away simply because it was in the opposite direction. The scan policy favors jobs whose requests are for tracks nearest to both innermost and outermost tracks. Suppose the head is at track 80 and is moving towards the outermost track, which is track 100. On its way, it serves the requests on tracks 85, 92, and 97. Then the head reaches the outermost track and changes direction. Again, assume that the queue is dynamic, and during this time more requests have arrived and some of them are on tracks 86, 91 and 97. So it serves the newly arrived requests on 97, then 91, then 86. So the tracks close to the outermost tracks are favored. The same situation will happen if you assume that the head is moving towards the innermost track. What we see here is the tracks nearest to the periphery track are served also when the head moves towards the periphery track and also when the head moves away from the periphery track. Again in scan, old requests that are in the middle of the disk may starve because newly arriving requests are located on tracks that scan favors. C-scan. The C-scan circular scan policy restricts scanning to one direction only. Thus, when the last track has been visited in one direction, the arm is returned to the opposite end of the disk and the scan begins again. Notice that when the arm returns to the opposite end, it does not serve any requests on its way back. This eliminates the bias of scan towards requests on tracks near the innermost or the outermost tracks of the disk. This reduces the maximum delay experienced by new requests on the other end of the disk. With scan, if the expected time for a scan from inner track to outer track is T, then the expected service interval for sectors at the periphery is 2T. With C-scan, the interval is on the order of T plus Smax, where Smax is the maximum seek time. In scan, we move from one end to the other, serving requests in T time. So we move from one end back to the same end, serving requests both when we are moving away and when we are coming back in 2T time. In C-scan, we move from one end to the other, serving requests in T time. When we get to the last pending request in this direction, we serve it in reverse direction, and then the head moves back to the other end in a period called Smax here. The example request queue and the question are the same as a scan, but we are asked to use C-scan to schedule these disk requests. The starting track is 100 and we are moving outward. So the next track is 150, 160, 184, and then we change our direction, but on the way back we will not serve any requests. So the next track is 18, 38, 39, 55, 58, and 90. The total tracks are 322. Average seek length is 35.78, and this is a bad seek length because you are moving over the entire disk without doing anything. This is how the head moves for C-scan. Problem with SSDF, scan and C-scan. It is possible that the arm may not move for a considerable period. If one or a few processes have high access rates to one track, they can monopolize the entire device by repeated requests to that track. High density multi-surface disks are more likely to be affected by this characteristic than lower density disks and or disks with only one or two surfaces. To avoid this arm stickiness, the disk request queue can be segmented, with one segment at a time being processed completely. N-step scan. The N-step scan policy segments the disk request queue into subqueues of length n. Subqueues are processed one at a time using scan. We are assuming n is 5 here. The first 5 requests are currently being processed according to scan. While a queue is being processed, new requests must be added to some other queue. So since the first 5 items are being processed, additions will not be made to the first 5 slots. If fewer than n requests are available at the end of a scan, then all of them are processed with the next scan. So once we are done with the first 5 requests, instead of processing the next 5 requests, we will process the next 7 requests with scan. With large values of n, the performance of n-step scan approaches that of scan. With a value of n equals 1, it degrades to FIFO. N-step scan eliminates starvation of old requests at the hands of new requests, which we saw in scan. F-scan. F-scan is a policy that uses two subqueues. When a scan begins, all the requests are in one of the queues with the other empty. During the scan, all new requests are put into the other queue. So all incoming requests will go to the queue that we have marked empty. Thus, service of new requests is deferred until all the old requests have been processed. Now we come to something very important, your homework. A disk has 200 tracks. The disk head is initially located at track 100. If required, the initial direction of the head should be assumed to be towards increasing track number. The requested tracks in the order received by the disk scheduler are 35, 47, 189, 170, 22, 134, 59, 12, 154, 129, 5, and 67. Use FIFO, SSDF, scan without look, scan with look, and C-scan to schedule these disk requests. Calculate the average seek length. Another idea important for I/O management is the disk cache. Cache memory. The term cache memory is usually used to apply to a memory that is smaller and faster than main memory and that is interposed between main memory and the processor. Cache memory reduces average memory access time by exploiting the principle of locality. Locality of reference, also known as the principle of locality, is the tendency of a processor to access the same set of memory locations repetitively over a short period of time. Disk cache. The principle of locality can be applied to disk memory. A disk cache is a buffer in main memory for disk sectors. The cache contains a copy of some of the sectors on the disk. When an I/O request is made for a particular sector, a check is made to determine if the sector is in the disk cache. If so, the request is satisfied via the cache. If not, the requested sector is read into the disk cache from the disk. Because of the phenomenon of locality of reference, when a block of data is fetched into the cache to satisfy a single I/O request, it is likely that there will be future references to that same block. Design considerations, consequences of a disk cache hit. When an I/O request is satisfied from the disk cache, the data in the disk cache must be delivered to the requesting process. This can be done either by transferring the block of data within main memory from the disk cache to memory assigned to the user process, or simply by using a shared memory capability and giving a pointer to the appropriate slot in the disk cache to the asking process. This saves the time of a memory to memory transfer and allows shared access by processes using the reader's writer's model. The data in the disk cache is a shared resource. The processes asking for it can either read it or write on it. Design considerations, replacement strategy. When a new sector is brought in, an existing block may need to be replaced. The most commonly used algorithm is least recently used or LRU. LRU dictates to replace that block that has been in the cache longest with no reference to it. Logically, the cache consists of a stack of blocks with the most recently referenced block on the top of the stack. When a block in the cache is referenced, it is moved from its existing position to the top of the stack. When a block is brought in from secondary memory, we remove or replace the block that is at the bottom of the stack from the disk cache to make space for the new block and push the incoming block onto the top of the stack. Continuing with design considerations and replacement strategy, another possibility is least frequently used or LFU, replace that block in the set that has experienced the fewest references. LFU is implemented by associating a counter with each block. When a block is brought in, it is assigned a count of 1. With each reference to the block, its count is incremented by 1. When replacement is required, the block with the smallest count is selected. LFU and LRU, which is better? Intuitively, LFU may seem more appropriate than LRU because LFU makes use of more pertinent information about each block in the selection process. A simple LFU algorithm has the following problem. It may be that certain blocks are referenced rarely overall, but when they are referenced, there are short intervals of repeated references due to locality, thus building up high reference counts. After such an interval is over, the reference count may be misleading. It will reflect that the block will be referenced again, but in truth, the block will not be used further. This causes LFU to make poor replacement choices. Frequency-based replacement. Frequency-based replacement is an amalgam of LFU and LRU because both the count and the stack are present here. The blocks are logically organized in a stack. A certain portion of the top part of the stack is designated the new section. When there is a cache hit, the referenced block is moved to the top of the stack. If the block was already in the new section, its reference count is not incremented. Otherwise, it is incremented by 1. Blocks in the new section are never replaced. This strategy achieves only slight improvement over LRU. Problem with frequency-based replacement. On a cache miss, when a new block is brought into the new section, its frequency count is 1. The count remains at 1 as long as the block remains in the new section. Eventually, the block ages out of the new section, that is, it gets pushed back until it becomes part of the old section with its count still at 1. If the block is not re-referenced fairly quickly, it is very likely to be replaced, but because it has the smallest reference count of those blocks that are not in the new section. In other words, before blocks pushed back into the old section can be re-referenced and can get a count greater than 1, they are replaced because they are part of the old section. Refinement of frequency-based replacement. Divide the stack into 3 sections: new, middle, and old. Reference counts are not incremented on blocks in the new section. Only blocks in the old section are eligible for replacement. Assuming a sufficiently large middle section, this allows relatively frequently referenced blocks a chance to build up their reference counts before becoming eligible for replacement, that is, before they are pushed back into the old section. Simulation studies indicate that this refined policy is significantly better than simple LRU or LFU. Replacement and write back. The replacement of a block can be on demand. A sector is replaced only when the slot is needed. Pre-planned. Several slots are released at a time. If a sector is brought into the cache and only read, it is not necessary to write it back when replacing it. If a sector is brought into the cache and written, it is necessary to write it back when replacing it. Pre-planned replacement happens when we need to write back sectors. We cluster the writing and use a scheduling policy to minimize seek time. Performance considerations. The issue of cache performance reduces itself to a question of whether a given miss ratio can be achieved. This will depend on the locality behavior of the disk references, the replacement algorithm, and other design factors. Principally, the miss ratio is a function of the size of the disk cache. The larger the disk cache, the lower is its miss ratio. The exact sequence of reference patterns plus related design issues such as block size have a profound influence on the performance achieved by a replacement strategy. Now I have a reading assignment for you. Since the article does not need any explanation and you can pick the concept easily yourself, I will leave the topic of RAID for you to read and understand by yourselves. So what did we gather so far? We conducted timing comparison of data transfers for different file allocations. We looked at various disk scheduling policies and analyzed them. We were introduced to the concept of disk cache. We looked at the design and performance considerations of disk cache. And in the end, the things that you need to do for me. You have to do the homework. You have to go through the reading assignment that I've set you. You have to read the book. You have to note all the questions that you have in your mind regarding whatever we discussed in this lecture and keep them with you during the online session. And if you have any suggestions relevant to content or quality of this lecture, you need to email them to me. Take care. Allah Hafiz.